Oh, I'm so excited. We're ready for the second law of thermodynamics, which really kind of is the third law. Because remember, I talked about that. The first law is really the zero law, and the second law is really the first law. I know it's confusing. So the second law, which is kind of like the third law, but we're going to call it the second law. Okay, we're going to call it the second law. The second law of thermodynamics is like law. Now, if you've taken chemistry, and I'm assuming most of you have, you might have learned about the first law of thermodynamics. You might have. Of course, you probably learned it as energy cannot be created or destroyed, only change of form, and you may or may not have used the equation for it. Some of you have, some of you haven't. But what you bet you haven't done, I bet you haven't done anything with the second law. You might have talked about the word entropy, but okay, okay, let's get into it. The second law has multiple versions of different ways to express it. Now, every version, the way you express the second law in multiple different ways, all mean the same thing. They do. They all mean the same thing, but there are different ways to show it. So what I'm going to do is I'm going to draw for you a schematic diagram of a heat engine. What? Wait a minute, what? What? Schematic diagram. Schematic diagram. That means it's kind of a representation. It's not the real thing. I'm going to draw a heat engine on the board. Now, most of you probably drove or drive a heat engine, or drive back and forth. You use a heat engine. It's like the automobile. Internal combustion engine is an example of a heat engine. It uses heat to do work, to turn stuff, to make the wheels on the bus go up and down. Wheels on the bus go up and down, up and down, up and down. Okay, remember the song? Wheels on the bus go up and down. So you know that you have to have heat produced. You may not have thought about it, but you do. That engine, that combustion engine, burning that gasoline, is producing a heat, which causes pistons to go through the expansion and move the thingy, which turns the drive shaft, which turns the wheels. Yeah, internal combustion is how things get done, people. How things. I don't drive I drive an electric. I drive a Chevy Volt. Yeah, that's no. Well, that is not an internal combustion engine. Okay, it's an electric engine. It's an electric vehicle. An electric engine, electric motor, is different than internal combustion. Okay, more on that later in different part of the course. But for now, let's stick with heat engines. Now, a schematic diagram of the heat engine, which, by the way, I have a nice little scanned photo for you. Yes, I do, of a heat engine. Okay, You want to have this, trust me, you're going to want this heat engine thing. So let me draw on the board for you. Okay, let's go seasonal here. Let's go. But I think this marker's kind of dying on me. So let's go with, I got a new one. Woo-hoo, yeah. Okay, Halloween, I love it, I love Halloween. Okay, so here we go. Schematic diagram of a heat engine. So a schematic diagram is a representation, and so here's my schematic. Now, it's just not going to, just give me a minute here, okay? If I were you, I'd be copying this down. Yes, I would. Yes, I would. Trust me, you're going to want to know this. I might just say, draw me a schematic diagram of a heat engine on whatever assessment that you're going to need to know that, okay? So do it. Do it now. Get through the chopper. Hang on, let me just do this. I'll do this first. What are you doing? I started drawing it. Sorry. Okay, let's do that. And then here, okay, and then here, let's see, let's throw this like that. So this comes down like that. Whoops. Can make that parallel. A nice drawing here. Parallel. Ah, that's not parallel. That's a terrible parallel. Better than that. Like that. Okay, now this part of it. Yeah, those are arrows. Okay, what the heck is that? That's a schematic diagram of a heat engine. You go out to your car, you go out there right now, and you would open up the hood of the car, that's exactly what you see. Go do it. Go look. Yeah, we'll wait. Okay, you back? You see that? Yeah, I did. See? Told you. That's inside your car. Okay, so that's the thing that makes your car go. All right, now, let's see. This part of it up here is called, and this part of it is called the heat source. The heat source. Heat source. All right, that's where the heat's going to come from. Okay. Now, this part of it, this part of it's hot. So we label this as TH, hot temperature, high temperature. Down here, this is called the environment. The environment. Environment. And this is the relatively speaking TC. Cold temperature. This is the hot temperature, the cold temperature. Now, from here to here, heat flows like this. That's one of the versions of the second law of thermodynamics. Heat flows from here to here, hot to cold. On the way, though, you can make it do some work. Yes, you can. You can make that heat energy do some work. In fact, this is the work part of the schematic diagram, the W part. Okay, so what is this showing? This shows that several different ways of stating the second law of thermodynamics. Let's write these down. First thing, my schematic diagram of any heat engine shows that you have high temperature stuff, a high temperature reservoir, and that goes to a cold temperature reservoir. But while it's going from hot to cold, you can do some work for it, get some useful work out of it, make the wheels go round or up and down depending on whether or not they're on the bus. The wheels on the bus go up and down, but the wheels in your car go round and round, okay? Yeah. So on the way we can make that energy do some work. Okay, so what we see out of this, though, are the different laws of thermodynamics. What? First of all, let me show you the first law. There's the first laws up here. No, it's not. I don't see the first law. I don't. It's there. This is your QH, and this is your QC. This is your hot heat, and this is your cold heat. That sounds kind of oxymoronic, doesn't it? Cold heat. What? Yeah, well, there's hot heat and cold heat, sure. What I mean by that is the heat in this room right now is probably about 68 degrees Fahrenheit, but outside it's kind of cold today, it's a cool day, so it's probably like 55 degrees. Well, there's hot heat here compared to outside, relatively speaking, cold heat out there. There's still heat out there. I mean, you can say, well, cold heat, that's kind of stupid. Well, even if it's cold, there has to be heat. If there wasn't any heat in a cold environment, what would the temperature be? Think about that. Okay, even cold, you know, cold like Siberia in the middle of January day has heat. If it didn't have any heat, it'd be like absolute zero cold. We don't have that. So there is cold heat. It's just not as much heat as hot heat. Okay. So we have cold heat, we have hot heat, and we have work. Second law of thermo. Here we go. Let's state the different ways. This shows a heat engine. An engine this is the engine part. So this is the engine part. This might be a heat source if it's your car. The heat source can be the gasoline. Okay, you combust the gasoline. Boom, you get a lot of energy out of gasoline when it combusts. And that is your hot heat produced from that gasoline that's combusting. While in the engine, it can now be used to do some work. Make those pistons go up and down. Turn your wheels. But at the same time, a lot of that heat gets tossed out into the environment. Yes, it does. You know that. Put your hand on top of the engine when it's running. Don't do that because you're going to get burned and I'm going to get blamed for it. I got to fill out paperwork and answer questions and clean up a mess. So don't do that. Let it professionals only, please. But if you put your heat on the hand, if you put your hand on the engine, you know it's hot. Engines, after you put your hood in the car, hot. Okay, take your hand and grab that tailpipe and hold on to it as long as you possibly can. Don't do that either. Okay, don't do that. You know that's hot stuff. That's wasted energy out to the environment. That energy just goes literally like out the window. It goes out into the environment. That energy didn't get used to make the wheels go around. Some of it just gets tossed out into the environment, not useful energy, but some of it does get used. Some does. The first law is shown right here. Energy cannot be created or destroyed, only changed in form, right? First law. First law, here's your total amount of heat. That's your total. QH is your total available heat. Some goes to W, some goes to the environment and gets wasted out to the environment. But if I add that plus that, guess what? It equals that. Yes, it does. So these two together show the first law, energy cannot be created or destroyed, only changed in form. From QH, we get W and QC. There's your first law, shown in this sweet drawing. And when I ask you to draw the schematic, draw it like this. Don't do this. Don't do this. Points, lose points. You take your QH, and here's your W, okay, and then you do this, and here's your QC, okay? Meh, big wrong, because you had your total amount of energy, and look, you got a lot more out of what you had. You can't do that. Okay, these two have got to total that. Make those two total that. I'll be looking. Yes. Don't equal that. No. Bad. Good. Bad. All right. So first law, shown. Second law. All right, here we go. This is the fun. Second law of thermo can be stated in multiple ways. Way number one. Heat always flows from hot to cold. Heat always flows from hot to cold. And my schematic diagram is showing that. It's showing heat going from the hot source out to the cold environment. It's showing hot to cold. So heat flows from hot. You still see this? Yeah, you can. To cold. All right, okay, all right. There's way number one. Way number one. That's one thing that my schematic diagram is showing the second law, that version of the second law. Hot to cold. Second thing it shows. Second version of the second law. Funny, second of the second. Heat engines cannot be 100% efficient. What? Yeah, heat engines, and that's what this is. It's a schematic of a heat engine. Any heat engine. Car, truck, plane, train, they're internal combustion engines. That's representing all of those. Heat engines cannot be 100% efficient. What the heck does that mean? What that means is you can't take all of this QH and make it do work. That would be 100% efficiency. Nothing wasted to the environment. And if that arrow just went like that, that would be 100% efficient. All the energy is going into work, and you would get nothing to the environment. Nope, wrong. That don't happen. Okay, cannot happen. There's always wasted heat energy. Feel the engine, feel the hood of the car, feel the tailpipe. There's always going to be random motion of those gases. Some of it's going to make pistons move. That's what you want out of it. That's your work. Some of it's going to go smashing into different things and just cause those things to get warm. And by those things getting warm, they're not doing any work. That's going to dissipate out to the environment. Okay, that is a law. Oh, I just dropped my, hang on. That's a law. A law. Oh, wait, we're going way over here because I'm trying to find, oh, there it is. Hello. All right, wait, come on back. What are you doing? I found it. All right, there you are. Okay, good. So no heat engine can be 100% efficient, okay? If you can make a 100% efficient heat engine, call me. Okay. All right, we'll be millionaires. Billionaires. Third version is kind of related to this one, okay? It essentially is the same thing as this one, but just done in a different wording. That you cannot, let's see, no heat engine can convert all QH to work. It's the same thing, essentially, but just saying it in a different way. But you can't get all your QH and make it go to work. If that were true, if all this did become this, you'd have 100% efficiency. And those are just kind of saying the same thing, but just from different ways of saying it. But, okay, stick with me. Here we go. One other thing that we have here is that entropy happens. Entropy happens. That one I'm going to go back and explain in the next video because this is getting kind of long. You're falling asleep. And stop that drooling. Stop it. I see you. I see you, Colby. I see you drooling there, Colby. Wake up. Thank you. Okay. We'll talk about this one. We'll tackle this one in just a minute on its own. So just trust me for now. Entropy happens, okay? That's what this is showing. And then the fifth thing, another version of the second law, what it's saying is that absolute zero cannot be achieved. Absolute zero cannot be achieved. You cannot get absolute zero. Why? Because heat always flows from hot to cold. And if you're trying to get absolute zero, you got to pull heat out of that environment that you're trying to get to be absolute zero. By pulling heat out, no matter what's going on inside, you're pulling the heat out. Heat on the outside of the environment is always going to go back in because it's cold in there. You start getting that environment inside that chamber that you want to make absolute zero. Well, it's pretty darn cold in there, and it's pretty darn warm, relatively speaking, on the other side of that thing that you're trying to make absolute zero. He's always going to flow back, hot to cold. Always goes back in. You can't get all the heat out. Okay, you're really close. I mean, like I'd call it like we got it right, but technically no, you cannot get absolute zero because of what happens here with heat flow. Okay. This video is almost 16 minutes long. We're going to shut this down for now. We're going to come back and we're going to tackle this one here in particular for you. Okay, take a break. Go get some water.